going to go through some very simple examples also. So there's many things we can do, and how we can use connected rate of change. And it's actually pretty simple to draw out information. So the first part of this question is the radius of the circle increases at a rate of 0.2 cm per second. Now from this part, okay, it already tells us one very important clue. That the radius, I'm going to use R. I like to use all these variables, R, T, so we need to actually state them later. But for now, just make some mental note that dr over dt is equals to 0.2. Okay, what we're trying to do here is to calculate the rate of increase in the area when the radius is 5. So if you are trying to find the rate of increase of the area, okay, when the radius is 5, what we are trying to find is, I'm going to use A as the area, dA over dt. Okay, so let's make some definitions. Let R be the radius, and the radius is a circle, right? So the area should be A, and A be equals to pi r square, be the area. Okay, so from here, what we're going to do is I want to find d over dt. Okay, so but because I have a equals to pi r square, I can find dA over dr, which is simply 2 pi r. Interestingly, what is 2 pi r? It's your circumference. Okay, but nevertheless, having that doesn't really help me. But what I'm trying to find is dA over dt. Right, that's what the question is asking. So dA over dt is dA over dr times dr over dt. Okay, and it's at r equals to 5. So dA over dr is 2 pi times 5 times dr over dt, which is what the question has shown us, is 0.2. So we have 0.2 times 10. So this will be 2 pi cm square per second. Right? We need to write the units here because this is a rate of change. We're going to figure out what is it. Okay? So it's a very, very, very simple example of how this goes. Now we move on a little bit tougher one, which is something like a hemisphere. Right? In this case, we have a hemisphere that is fully completed, completely filled with water with a radius of 8 cm. And then we have water that is transferred at a steady rate into an empty inverted right circular cone. Wow, there's a lot of things here. But what is essentially going on is that there is water filled in that thing over there. Okay, I'm just going to like use the same thing. Okay, what is being filled is being poured into a cone over here, and the cone also has a radius of 8 cm. Okay, this has a radius of 8 cm, not the best 8 cm, and it has a vertical height of 16 cm. Okay, so we're going to pour from the hemisphere to the conic cone. Now, given that all the water is transferred in 5 1/3 seconds and v cm cube represents the amount of water in the cone at any time t, find dv over dt in terms of pi. Okay, so we have here that the water is transferred in 5 1/3 seconds, right? And 5 1/3 seconds is the time, right? The total time taken. Okay, so what I'm going to do is very simple. V represents the amount of water in the cone at any time t. So very simple. Because we don't really know the height of the. Oh, actually we do know. Actually we do know one thing. Number one, we can actually easily tell what is the total volume of water actually. So what's the total volume of water? Okay, the height here is actually still 8 cm, right? Because it's a hemispherical bowl, right? So we can easily find the volume of water that inside here. But so the total volume of water is in fact equals to the volume of the hemisphere, right? So the volume of the hemisphere is 2 over 3 pi r cubed, which is 8 cubed. Okay, I'll definitely need my calculator here. It's going to be a bit tough to do this without a calculator. So 8 cubed times 2/3. Okay, we're going to get a fraction. This is 1024 over 3 pi cm cube. Yes. Okay. So what's dv over dt? Remember, dv over dt is the rate of change, right? So we can take the total volume divided by the total time taken, which is 5/1/3. So dv over dt can be written as total volume divided by total time. Correct? Because the definition of dv over dt is the rate of change of the volume with respect to time. So we can, if we have the volume, we have the total time, we can easily figure that out. So that will be 1024 over 3 pi divided by 5/1/3. Okay, but I don't really like to use mixed numbers here. So in this case, this will be 16 over 3. Right? What is 16 over 3? Right? See, this guy is 16 over 3. Okay, so it's the total volume divided by total time. Now from here, you will do your calculations and you realize that you'll get a pretty nice number. You're going to get 64 pi cm cube per second. So this question forces you to create the dv over dt on your own. Okay, then we can find the rate of change. Now we're going to find that the rate of change of the height of water level. Okay, so the height of water level is very simple. Okay, so what is the volume V? Okay, that's V is the volume of the cone. We know the maximum height of the cone and we know the maximum radius of the cone. However, when the water is being poured inside, we cannot assume that it will fill up it completely, right? So there's an unknown R and an unknown H. Okay, what we're gonna do is, number one, let's say in this question, okay, I have, okay, at any time I have a height H and a height R. By proportion, in fact, we can say that R, the radius and the height, okay, by proportion, right? You mentioned that by proportion over here, if I connect this all the way up, okay, when the radius is in fact half of the height, and it kind of like increases proportionally lah, in some sense. So I can say that the height here, h, is equals to 2r. Okay, now so we want v to be equals to 1/3 of pi r square times h, where r is the radius and h is the height at any time t. This is a very important definition. Okay, based on the, okay, how can we say based on the maximum height and the maximum radius, we can use similar triangle because this is right angle, right? By similar triangles, we can connect the radius and the height, right? The height will always be 2 times of the radius. So therefore, since r equals to 8 when h equals to 16, okay, we can form a relationship here. The height is equals to 2 times of r. Okay, so from here, v is simply 1/3 pi r square times h, which is equals to 1/3 pi r square times 2r. Okay, which actually gives us 2/3 pi r cube. Oh, isn't this just the volume of a hemisphere? Right? Pretty interesting, right? But our question here is to find the height of the water level. Okay, so we are not interested in this. I'm not interested in this. Okay, I want to find the height, right? So in fact, I'm going to redo this. R is equals to h over 2. Instead of changing r, instead of changing h, I will change r. So this will be h over 2 square times h. That makes things very interesting for us because we have 1/12 pi h cube. Okay, and so let's figure that out. We have dv over dh, and this is equals to 1/12 pi times 3h squared. Now from here, you will have 1/4 pi h squared. To figure out dh over dt, which is what the rate of change of the height, right? I can actually use dh over dv times dv over dt. Okay, what is the height? We don't know, but we know that we do know the depth of the water is actually 6 cm. So we can say at h equals to 6. Okay, so what is this guy over here? So this guy is actually pi h square over 4. If you want to flip it up, so if dv over dh is pi h square over 4, dh over dv will be just the reciprocal, 4 pi h square. Okay, what is dv over dt? We found it earlier, which is 64 pi. H square is 6, so we have 4 divided by pi times 6 square times 64 pi. You do your calculations, the pi will cancel out. We have 64 times 4 divided by 36. You're going to get 64 over 9 cm per second. Okay, so pretty interesting question over here. So this is part A. Right, part A. Now the second part is you want to find the horizontal surface area of the cone. Oh, so the horizontal surface area of the cone is actually connected by the radius, right? So for part B, it's going to be interesting because the horizontal surface area is the top part of the water here. So just imagine, I'll draw another cone here, right? So this area is also increasing, but it's increasing by A equals to pi r square. Alright, what do we have to do with this? Honestly, it's not going to be very easy here, because if we want to use the area, okay, we need to kind of connect the area and the volume. Not that straightforward, I would say, right? So what we're going to do over here, we are going to just find what's dA over dr. Okay, what's d over dr? This is simply 2 pi r. Okay, why do we need dA over dr? Because essentially later, if we want to find dA over dt, we want to have dA over dr times dr over dt. So this would mean that we need to figure out what is dr over dt. So that leaves us with part B. Since we have 1/3 volume equals 1/3 pi r square times height, this can be written as 1/3 pi r square times 2r, okay, because h is equals to 2r, and this will give us 2 over 3 pi r cubed. Now from here, dv over dr will simply be, I'm going to shortcut this will simply be 2 pi r square, okay, and then we can find dr over dt is equals to dr over dv times dv over dt. Right, so this is going to be a very long-winded way here. So dr over dv is 1 over 2 pi r square, and dv over is 64 pi. Okay, we do our calculations, you will essentially get 32 over r square for dr over dt. Hence, let's put it back here. This is 2 pi r, and this is 32 over r square, and this is at the depth is 6, right? So if the depth is 6, the radius will be 3, right? Because the radius is half of the depth. So at r equals to 3, we have 6 pi times 32 over 9. So 32 times 6 divided by 9, you have 64 over 3 pi cm square per second. Okay, it's a very, very long-winded solution using multiple chain rules and connecting it with volume, area, and so on and so forth. But that is the point of rate of change. We want to connect all the way back to the topics of volume and area and figure out how fast is it changing at the time. How fast is the length changing? How fast is the area changing? And how fast is the volume changing? Okay, so I'll leave you here.